Hello and welcome to Wagner Academy. This is Geometry Lesson 1.3. We're talking about distance and midpoints with this lesson. This is some of the new terminology that you should know by the end of this lesson. A lot of this you may have heard of before in algebra or pre-algebra. Make sure you know all these things though by the end. Come back and check that list. Make sure you got it down. And also make sure if you're one of my students, use those extra examples in your book. Well, let's get started. It says the distance formula is up here for a number line and in the coordinate plane. So a number line is just one-dimensional, just along the line. And then the coordinate plane is like this. You've got the x-axis, y-axis, the origin. We've got coordinate points on the coordinate plane. So on a number line, the distance formula for any 2 points, P and Q, that have coordinates at A and B, those coordinates can be used to find the distance between those 2 points. So B minus A, make that look a little more like an A and less like a 9. There we go. The absolute value of B minus A, or you can reverse the order and do the absolute value of A minus B. The absolute value makes it so that the order you put them in doesn't matter. And for the distance D between 2 points with coordinates x1, y1, this should look familiar, I think, from algebra. X1, y1, and x2, y2. And notice this is a little subscript. This is not a big number 2. It's a small number 2 written as a subscript right next to the larger x and y letters there. So this is given by the distance formula for two-dimensional coordinate plane points. This is, see if this looks familiar. Do you remember this from algebra? Y2 minus y1 squared, in other words the difference in the y values squared, plus x2 minus x1 squared, in other words the difference in the x values squared. And this formula right here is based on something that I'm going to keep it a secret from now. It's based on something that we're going to check out later on in this lesson. But we're going to use these formulas. Personally, I prefer this one for a number line, doing the farther to the right coordinate first. That way, if I forget about the absolute value, or if I don't even want to use the absolute value, I don't have to. So I prefer this one. Both of them work though, as long as you use the absolute value. So with example 1, suppose J and K are coordinates on a number line at -2 and 3 respectively. So it looks like J, since it's first, that's at -2. I'm going to say this is at 0. And then this would be -2 right here. This would be 2 right here. This would be 3 right there then. So I'll fill in the rest here. We've got a 1, 2, and 3 going this way. -1, -2, -3 going that way. And J and K, J was at -2. And no, I'm not JK. Not just kidding. Oh dear, Mr. Wagner. Okay, moving on. Plot the points. We did that on the number line. And find JK. So JK means, from lesson 1.2, hopefully we remember, that's the distance between those 2 points, between J and K. So we can use this formula right here, B minus A. I can pick, I'm going to go with B being the rightmost coordinate, so it's 3 minus, and then my A is the leftmost coordinate, so minus a -2. The formula itself has a negative sign in it, and then if you have a negative number, you have to subtract that negative number. So this would equal 3. Anytime you see a minus a negative, we change that to a positive. So 3 plus 2, that's the absolute value of 5, and that is just 5. So that is our final answer. A simple example to start. Should be pretty easy when you have one-dimensional things on the number line like that. Coordinate plane, a little tougher. Let's check one out like that. Example 2, plot B at 4, 2. Okay, I'm going to do that first here. 1, 2, 3, 4, and up 2. There's point B right there. And G is at -3, -1. So back 3, down 1. There's G right there. On the coordinate plane. So we did that. Now we're going to find BG. I'm going to have a couple different methods, a couple different ways we're going to do this. The first one is the distance formula, which we just saw in the previous slide. And the second method, I'm still going to keep it a secret, but this is a hint over here. This picture, this is a man that will come to know, or at least come to know one of his theorems, hint hint, very well. I'm going to draw a straight line here a moment, or better yet, I would say a segment or line segment, so it doesn't go on forever. I just have the segment connecting G and B. So the distance formula, I could use that, and I could label these points. I think this is a great idea. I'm going to use a different color here. Good idea, I think, to use that whenever I do. So x1 is my first x coordinate. I'm going to go with B being my first x and first y coordinate. So this I'm going to call x1, y1 right here. This one I'm going to call x2 and y2. And if I do that, I always like to write the formula out in the general way first, and then just plug in the values that I know after that. It makes it really easy. So I've got y2 minus y1 squared, difference in the y value squared, plus the difference in the x values squared, the square root of all of that. So where is that formula coming from again? That's from right here. So this formula works for any two coordinate points to find the distance between those 2 points. Looks like we have y2 as -1. So I'm plugging in place of y2, the second y coordinate, that's -1. I've got that minus 2, and I'm squaring that, plus -3 minus 4 squared. If one of these values was a negative, I would have to have minus a negative, which would become a positive. However, they're not negative, so it looks like that. And if I continue to simplify this, I've got -3 squared plus -7 squared. 3 squared, or -3 squared, is the same as 3 squared. You're going to get 9. And -7, same as +7 squared after you square it. That would be 49. And if we add those things together, we've got the square root of 58. That would be a final exact answer. And I approximated this in a calculator earlier, and I got about 7.62 as an approximate answer, rounded to the nearest hundredth. So this is one method, method 1. The second method, have you guessed who this guy is? This is Pythagoras. The second method is the Pythagorean theorem. So this is a theorem named in his honor. Pythagorean theorem. Do you remember what it is from a previous class? I hope so. It's leg squared plus leg squared equals hypotenuse squared. That's the way I prefer to say it, but you may have heard of a squared plus b squared equals c squared. That's fine if you remember it like that, as long as you remember that a and b are the legs and that c is the hypotenuse. So I'm going to write it like that instead here, and I'm going to use a different color once again to show you that this isn't actually part of the segment. It's just something that's going to help me use the Pythagorean theorem, or determine what to plug in for the Pythagorean theorem. So the distance formula, it comes from the Pythagorean theorem. It comes from the idea that we can make a right triangle like this, and then this is the hypotenuse, what we're looking for, BG, and these are the two legs. The legs make up the right angle. The hypotenuse is always across from the right angle, and it's always the longest side. So if I just count the number of jumps, the number of marks here, I'm going to know how long the legs are. This is 1, 2, 3 down this way. I'm going from a y value of 2 down to a y value of -1. And 3, oh, look at that. There's -3. After I square it, it became +9. Same thing's going to happen over here. In a like manner, this way, it's 7. So if you go from -3 to +4, that's the difference in the x values. And this was the difference in the y values. So now if I plug those values in to the formula, I've got leg squared plus leg squared equals hypotenuse squared. That would become 3 squared plus 7 squared equals, my hypotenuse is what I'm looking for, BG. So it's BG squared. So this is 9, and this is 58. Well, that looks familiar. Not 58, I'm sorry. This is 9. I'm getting ahead of myself there. And 49. If I add those together, I'll get 58. So that looks familiar. There it is right there. Where does the square root part come from though? Well, I have to get rid of this squared. I want just bg, not bg squared. So I'm going to take the square root of both sides at that point. So the square root of 9 plus 49 would be the same thing as the square root of 58. And square roots and squares are inverses of each other. They're going to undo each other, leaving me with what I wanted, with bg. And that, again, was approximately 7.62. So either way I do it, I'm going to get the same answer. There are just two valid ways to do the same thing. Depending on the situation, you may find the distance formula easier to use. If they don't give you a picture and they just give you two coordinate points, sometimes that's easier to use. Other times, I think especially when they give you the picture, the Pythagorean theorem is, in my opinion, much easier to use. So know how to do both methods. If I don't tell you, or if whatever you're working on doesn't give you directions saying you have to use a particular method, you can use either one, whatever you're more comfortable with. Example 3, we'll get to that in a second. We've got a couple more things to talk about before we get there. So now the midpoint. Now instead of the distance of segments, we're talking about the midpoint of a segment. Is exactly, well, it's in the middle, it's halfway between the endpoints of a segment. And if M is the midpoint of PQ, and that's segment PQ, so don't forget your little segment mark above those two letters, then this would be true. You would have PM, the distance from P to M, plus the distance from M to Q would have to equal the distance from P all the way to Q. So this picture kind of shows you that, and it shows you that here too. These pictures showing that M, this is saying that M is the midpoint in both these pictures. M is the midpoint, so PM plus MQ would equal the whole thing, PQ. Same thing over here, PM plus MQ equals the whole thing, PQ. For a number line, the formula for the midpoint is pretty simple. You just take the coordinates and you find halfway in between those coordinates. So you add them up, A plus B, and you divide that by 2. It's the average of the coordinate values, in other words. And really the same thing works here for the coordinate plane. You're taking the average of the x values and the average of the y values. That's where your midpoint's going to be. So this point right here, this coordinate point, would be x1 plus x2 divided by 2, the average of the x values, and a comma, that's the x coordinate for the midpoint, and then a y1 plus y2, the average of the y values, dividing that by 2. So that's what that point is right there. So those are the basic ideas we use for a number line and for coordinate planes with midpoints. So example 3 now, on a number line, suppose the coordinates of A and Y are negative 25 and 63 respectively. So A, I'm going to say, is right here at negative 25, and Y, I'm going to say, is over here. I know it's a positive number. It's going to be larger than negative 25. It's going to be over there, and M is supposed to be the midpoint of AY. So I know, put a little dot there, there's Y. I know the midpoint is going to be halfway in between, and I know that this would be true. I know that this would be congruent to this right there. So I'm going to mark that on my picture, and yep, I spelled the name there. So I might spell your name eventually, who knows, when I'm doing these things. But Amy, this is a shout out to you, whoever is an Amy out there watching this video. We've got the midpoint M. We just used this formula right here. So I'm going to take my two coordinate values, negative 25 and 63, and I'm going to add them together and then divide by 2. It's the average of those two values, negative 25 plus 63 divided by 2. This would end up being 38. We divide 38 by 2 and we get 19. So that means right over here, this point would actually be at 19. Continuing with example 4, find the coordinates of M, the midpoint of TI, for T, negative 3, 0, and I, 2, 4. So for this one, we're going to use this idea. We've got x1 plus x2 over 2, y1 plus y2 over 2. Let's label these points with those particular values. I'll use a different color for that. So I've got x1. I wanted to go with red. I meant to do that. I thought I clicked it. There we go. x1 for -3, y1 first y coordinate at 0, and then this will be x2 second x coordinate and second y coordinate, 2 and 4. Let's plot those points on this graph. This is here to help us figure this out. So -3, 0, that's t, and 2, 4 would be up here. I'm going to squeeze that in there. 2, 4, that is I right there. So this is I at 2, 4. And this is t at -3, 0. So it looks like our midpoint is going to fall somewhere about here, I would say. I can't tell exactly where it is right now, but I'd say right about there. So it's halfway in between the x values and halfway in between the y values. We can use that midpoint formula to figure out exactly where that's going to be. So we have that m is equal to, I'm going to write the general formula out again. This is something that you don't have to do, but I think it's a good habit to get into, to write the general form every time. And then that way you just, again, plug in the numbers after that. So this is my x coordinate, it will be that. My y coordinate, y coordinate will be that. And let's plug in the numbers. So I labeled them to make it really easy for us to do here. So -3 plus 2. Get that over 2. And then I have y1, that's 0. y2 is 4. So 0 plus 4 over 2. And then just simplify those fractions. We've got -1 on the top here over 2. And this one we have 4 over 2. -1 over 2 doesn't simplify anymore, so I can just leave it like that. -1 over 2, I can just write the negative sign out in front. It means the same thing, or it's equal to the same thing. 4 divided by 2, however, is 2. It can be reduced down, simplified to that. So it looks like this is the midpoint m. If we look at our picture, if we go -1/2 over and then up 2, does it look like that matches up on the picture? Does it look like that's where it's supposed to be? Yes, so that's a good way to check our answer. Go back to the picture. If they didn't give you a graph, it would be a good idea to draw a graph and just to check and see that it's a sensible or reasonable answer. And being the midpoint, we know that this would be congruent Tm to Mi. Is that TMI too much information? Oh gosh. JK, TMI. Give it up, Mr. Wagner. Okay, find the coordinates of x. If y at 2, -1 is the midpoint of xz, and z has coordinates -1, -3. I meant to have this up here. I think I moved the line. Whoa, don't want to do that. Just that one. Grab that one. There we go. That's better. All right. So that should be right there is the midpoint of xz, segment xz, and z has coordinates -1, -3. So I'm going to plot -1, -1 positive 3, excuse me. -1 positive 3 is right here. That is my z coordinate. When I draw z's, I always put a little line when I'm doing math so it doesn't look like a 2. So a good habit to get into so that I don't think that you're writing a 2, that you're writing a z instead of a 2 there. So this is one of the endpoints. Z is at there, right there. Y is the midpoint. So this is the midpoint of segment xz. So 2, -1 over 2, down 1. This apparently is the midpoint of this whole segment. So when I know x is going to be on the other side going down this way of y. So we've got a segment connecting here. X is somewhere down in this range, it looks like. This is y at 2, -1. I'll use my straight line drawing tool. I've got that portion, that half of the segment right there. And then this is going to continue down in this direction, but I don't know exactly where it's going to end up. So going down this way, x is somewhere down there. How can I calculate this? I'll show you the algebraic way, and then I'll show you the graphical way, or the way to do that using the graph. So we can use the same formula. It's not going to change. The midpoint formula is still valid here. So I'm going to write that down again. Write a little small on this one. It'll be a little more work than we had up here. So don't write too big. If you write the same size approximately as I am, you'll be fine. So let's start off with that again. The general formula is right there. This time I actually know this value. I know what m is. So I'll color code in here again. Good idea. I've got this is the midpoint. So I know it is the midpoint. That means I can replace this value right there. I can replace m with 2, -1. So I'm going to do that here. I've got 2, -1. That coordinate point has to equal this coordinate point. And I'm going to call this is x1. I'm squeezing this in here, x1. And this one is y1. So my first x coordinate, my first y coordinate, is going to be these values right here. This is x1, y1. And I'm plugging those in. I know x1 is then -1. I don't know what the x2 value is. My second x value, that's the coordinates, the x coordinate of capital point x. So I've got this, and then a comma, and then my y1 value was 3. I've got that plus y2, my second y coordinate, which is the y coordinate for this point x. So at this point, I have 2 is represented by this value, -1 plus x2 over 2. -1 is represented by this value. So I'm going to separate this now into two different problems. I've got 2 must equal, why don't I write this? So 2, there we go, must equal -1 plus x2. And again, that's a subscript, so it's smaller than the x itself, written a little beneath it, a little to the lower right-hand corner of it. So this would equal 2. 2 would equal -1 plus x2 over 2. And we'd have -1. The y-coordinate would equal the y-coordinate here, 3 plus y2 over 2. From there, it's a matter of using some of our algebra techniques that we learned in Algebra 1 and perhaps in pre-algebra as well, trying to get x2 and y2 by themselves. So I'm going to, since this is divided by 2, if I multiply both sides by 2, that'll get rid of the divided by 2. It's going to undo that, get rid of the fractions. I like getting rid of fractions because it just makes it so much easier. Don't you think? Fractions, as long as we know how to deal with them, aren't that bad, but I'd rather not deal with them if I don't have to. So this becomes 4 equals, I'll put a little line here to separate the two problems. 4 equals -1 plus x2. On this side, it's -2 equals 3 plus y2. And from there, got one step left in both of them. Just add 1 in this equation and subtract 3 in this one. That gets me the x2 by itself here. This would cancel. It's going to get me y2 by itself over here. That would cancel. And so here I'm left with 5 equals x2. That's a really important thing. I'm going to circle. You may have noticed that I like to circle important things and then box in my final answer. Good habit, I think, to get into. So this -5 would be my y coordinate for the other endpoint. So I've got this and this giving me my final endpoint. I've got 5, -5 down here. This is my final answer. So x, my other coordinate, my other endpoint coordinate, find the coordinates of x. Y was the midpoint, x was one of the endpoints, x is the other, z was one of the endpoints, excuse me, and x was the other endpoint. So I've got 5, -5 right there. This would continue down this way. So this being the midpoint, y is being the midpoint here, is congruent to this. This is my final answer. So I told you I was going to show you graphically how this would work as well. So look here, color coding again, to make it easier to see. Look at this triangle. This is down 4, right 3. If you just copy that right triangle down here, so go from the midpoint and then go down, copying that triangle down and across that same distance, 4 and 3, you'll have your other endpoint. So if you want to use that instead, if this works for you and you don't want to do this, and graphically you can see how far down and how far to the left or right you're going, use that instead. That's totally fine with me. So really two different methods to do the same problem. I definitely prefer this if these coordinates are easy to deal with. If you have some crazy decimals or fractions, then maybe you want to depend on the algebraic method more. But if you want to just use this and copy the triangle twice to find that other endpoint, that works just as well. And this is the final slide here for this one. We've got example 5. What is the measure of segment ST if A is the midpoint of ST? So if it's the midpoint of ST, this would be congruent to this. And if things are congruent, that means they're equal in length. That means we could say that SA equals AT. That's a step you could skip and just go right to this. Say 8x minus 3 equals 5x plus 2 if you get good enough at it. But for the sake of the notes, I want to show you where this stuff is coming from. So SA would have to equal AT if it's the midpoint. And perhaps that's a test you're going to take sometime soon in the next year or 2 or 3 of the SAT. Good luck on that. If you do, this is going to help you actually do better on the SAT. Questions like these, we're going to be learning about things that show up on the SAT. So subtracting 5x, why did I do that? Well, I want to move the x's on one side, and then I got the x's on the left side now. I'm going to move the regular numbers, the integers, on the other side, move them over there. So that would cancel, and I'd be left with a 3x. This is gone. Bring down my equal sign, that's gone, equals 5. From there, can divide both sides by 3, and you might say, oh, Mr. Wagner, that's a fraction. Can that be right? That can't be right. We can't have fractions as answers, can we? Sure we can. Sometimes that happens, so I wanted to make a point of that on this one. Is it possible to have a fraction as answer? Yes. Is this my final answer? I started to box that in, and I almost had to yell at myself there. Good thing that I erased that. So this is important, very important, to figure out the answer to the question, but it says what is the measure of ST? It doesn't tell me solve for x. I have to do that to figure out what it is, but it says that I need to, in the end, find what ST is. So this is 5/3 or 1 2/3. What is ST going to be then? Well, I would add these two together. So I would have ST being SA plus AT. And I'm just going to plug in the value right away there. So I've got ST is equal to, SA is 8x minus 3. I just solved for x and got 5/3. So I'm going to plug that in for x. So I have 8 times 5/3 minus 3. That's from S to A. And then from A to T, I would be adding to that 5 times 5/3 plus 2. Now you could have just multiplied 8x minus 3 times 2 or 5x plus 2 times 2 since these values are the same. I'm going to go with this though, because if I do this, if I made a mistake back here somewhere, this would help me catch that mistake. Some of you may like to do this when you're multiplying fractions. Put those values over 1. If that helps you, then you can just think of multiplying straight across. Go ahead and do that. So this would be 40 over 3 for 8 times 5/3. And then if I want to add and subtract fractions, I have to get common denominators. So 3 is the same thing as 9 divided by 3, 9 over 3. So I can write 3 as that. This would be 25 over 3. And 2 I could write as 6 over 3. Once I have a common denominator, it stays the same on the bottom, and I just just add and subtract the tops from there. So 40 minus 9 is 31. 31 plus 25, that's going to be 56. And 56 plus 6 is 62. So you could say 62 thirds, or that would be equivalent to, as a mixed number, 20 and 2 thirds. Both of those answers, totally valid ways to get that. And if you plugged in, if you just did this part, 40 thirds minus 9 thirds, that'd be 31 thirds. And 25 thirds plus 6 thirds would also be 31 thirds. That should make sense because this point A was supposed to be the midpoint. These are supposed to be the same length, SA and AT. Awesome. Let's move on to our last little idea here. Any segment, line, or plane that intersects a segment at its midpoint is called a segment bisector. So if you hear that term bisector, you should think of cutting in half. So it's cutting a segment in half. And if we look at this picture here, assuming E is the midpoint of YK, segment YK, okay, if that's the midpoint, I'm going to do this. I'm going to put this on the drawing. That's congruent to that. Name as many segment bisectors as possible in the picture to the right. So here's our picture to the right, and this is the way our book defines it. Any segment, line, or plane. I might add ray in there as well, but since our book doesn't use ray, we'll keep the rays out, and I'll just make a mention of what ray might also be a bisector here. But NE, segment NE, that would definitely be a segment that intersects segment YK at its midpoint. E is the midpoint, and NE includes that midpoint. So that's one possibility. Another possibility could be segment OE, just the portion of the line that I see connecting these 2 points, but segment OE would also be a valid segment bisector. You could also say line OE, since there's actually a line going through those 2 points forever in both directions, so that would also work. And the only other thing I see, other than if I said ray EO, I feel like that would be a valid bisector as well. But again, since they're not saying rays in our book, I'll leave that one out or off our list here. But we could say a plane, this plane D, that's a cursive D again. We use script letters, remember, for that. Let's get my cursive on here. Woo! Look at that. That's a nice cursive D right there. So plane D also works. And if you can figure out why there's a picture of donkey in this slide, props to you. You can mention in the comments, I suppose, if you really want to. Yeah, that does it for us. Midpoints, we talked about how to find those, and distances. So distance formulas and midpoint formulas, the big ideas here in lesson 1.3. Here's those terms again, new terminology or review terminology that's important for this lesson. Make sure you understand those things. Our adventure continues in the world of geometry 1.4. I'll see you later for that one.